Okay, folks, we're going to look at the notion of counting using bit strings. Okay, so what is a bit string? A bit string is short for a binary digit. So a bit string is a string of zeros and noughts that are put together and used to count things with. Okay, so of all the following, if we look at that, 1001, that's a bit string that has 4 elements in it. Naught is a bit string with 1 element. There's a bit string with 4 elements, and here's one with 10, 2, 4, 6, 8, 10. Now that we call the length of the bit string. Okay, and we will write it as, for the first one, we will write it as B4. For this one it's B, and the B4 has the 4s at the top of the B. You'll see now over here, down here. We're going to talk more about that. We can also ask how many bits have ones or are ones. The number of ones in a string is called the weight of the string, and we indicate that at the bottom of the notation that we are going to use. Okay, so let's have a look. What is bit strings all about? The length is the number of noughts or zeros that are stringed together. So length 4, length 1, length 4, length 10. The weight here is 2. The weight there is 0. There is no 1. The weight there is 4. And the weight here is 5 because there's 5 ones. So for bit strings, a n bit string is a bit string of length n. So it means it has n noughts and zeros that are put together to form the bit string. Okay? Contains n symbols, each of which could be a naught or a 1. The weight of the bit string is the number of ones that we find in the bit string. B with the end at the top is the set of all n bit strings. So if I want bit strings that has a length of 4, then I will write it as B with a 4 at the top. But if I want the bit string with a weight of 4, a length of 4, to have a weight of 2, then I'll say B4 2. Okay, because then the weight tells us how many ones appears in the bit string. So for example here, the B32 that I've got down there, there's 3 bits in this bit string of which 2 of them are 1. So you can see it's 011, 101 or 110. There's only 3 possibilities there. Okay, but it must have a weight of 2. And if I only have 3 elements to choose from, then there can only be 1 naught in this string. Okay, so the counting question is, how many bit strings have a length of 5? How many of them, of those, have a weight of 3? So the number of bit strings that has a weight of 5, that's what I'm looking for. I'm looking for B5 and I'm looking for B53. So those with a length of 5 and 3 ones in them. Here I'm just looking for those that has a length of 5. Okay, bit string with length 5. So remember the yes-no idea again. Okay, there's 2 options. I either include you or I don't include you, but I need to include 5 numbers. So it's simple to get the length of the bit string. The length of the bit string here is going to be, or the cardinality as we're going to call it, it's going to be 32. It's 2 to the power of 5. Okay, so to find the number of 5 bits is straightforward. We have 5 bits and each of them is going to be a naught or a 1. Okay, we have that choice to make. So there's 2 choices for the first bit, 2 for the second and 2 for the third, and so on. So the number of choices you have is 32. So you can form 32 bit strings with a total length of 5. Finding the number of 5 bit strings with a weight of 4 is a little bit harder. Okay, now let's think of how you would do this. If the weight is 3, it means we have 3 ones in that bit string. Okay, and there's only 5, so 0, 0, 1, 1, 1 could be an option. 0, 1, 1, 1, 0. You can see you can play around and move those ones around in quite a few ways. Okay, so let's see. Once I've made my first choice, so let's say my first choice was a 1. Okay, remember I have a bit string of length 4. Let me just move myself away there. I have a bit string of length 5. I've chosen the 1 over here. Now I've got a choice of either 0 or 1 over here. Now if I had chosen a 0, okay, I only have 2 ones left, and I have 1 more 0 left to place. So I can place the 1 there, the other one here, and then I only have a choice of 0. So that is one of those with a length of 5 and a weight of 3. Okay, so I've got to choose for 5 positions. So after I've chosen the first position, for which I had 5 choices, I have to choose the second remaining positions to fill with zeros or with ones. Okay, so what do I have left? If there was a 1 here, I had 2 ones to put in the remaining part, and I had 0 ones to fill then the slots that weren't filled. If I had started with a 0, I still had 3 ones that I could work with, and only 1 0 to work with. I said 1, 2 zeros. Here I had 2 ones left, and here I had 2 zeros left to work with, to fill in my bit string. Okay, so you can see there's something interesting that's happening here. I've got the 3 ones, I've got 2 zeros. If I chose a 0 here, I've got 1 left to place, 1 0 left to place, but I still have 3 ones that I can place on. So let's read through it and see how they explain this to us. They say, finding the 5-digit number of weight 3 is harder. Thinking about how such a string could start, the first bit can be either a 0 or a 1. In the first case, the string starts with a 0. Okay, if we start with a 0, then we must then decide on 4 more bits over here. To have a total of 3 ones, among those 4 remaining bits, there must be 3 ones. So on the 4 remaining bits, we must have 3 ones. If we started with a 0, okay? So to count all of these, that is what the case is, the first case. In the second case, if we had started like we did here with a 1, then the remaining 4 bits must have a weight of 2. So to form the bit string with 5 elements and a weight of 3, I can do it in if I now talk about the cardinality of these sets, it will be the cardinality of this set plus the cardinality of that set that will give me the cardinality of the actual set of how I can choose to do this. Okay, so the strings in B54 all have the form, and this is the form that we applied over here. For the first one, I have for this one rather, the second one, where I chose my 1 first, I had 2 ones left to choose. So that is a 1 followed by a bit string of B42. Or if I had a 0 here first, then I would still have 3 of the 1s to place. Now folks, these two sets are completely disjoint. That means the one cannot happen whilst the other one is happening. They are happening completely separately. So that is why we can use the additive principle here. Okay, so to complete that distribution for us. Okay, so let's have a look here. This here, they say, is an example of a recurrence relationship. Okay, now we need to know what that means. That we represented one instance of our counting problem in terms of two simpler instances of the problem. If only we knew the cardinalities of those two sets. Now remember, the cardinality of a set is the number of elements that is in that set, that lies in that set. Okay, so repeating the same reasoning, they bring us to this component over here. So not knowing the cardinalities there, they say, well, how will we get B4? So in other words, there's 4, a length of 4 and a weight of 2 in this set. Okay, now if I chose the 1 first, then there's 3 elements left to choose, of which I can choose only 1. Which will, sorry, there's 3 elements left, of which one of those elements can be 1. Or if I chose the 0 first, then certainly there's still 3 elements left, but there's 2 1s that must be placed. So in terms of the cardinality of the set will be this cardinality here will be the cardinality of the bit set, the bit string with a weight, a length of 3 and a weight of 1, plus the cardinality of the bit string with a weight of 2 and a length of 3 will give me those two. Okay, now if you remember, the other alternative we had was B, 4 and 3. So how could we have done this? Well, we could have chosen the 0 first, then we had 3 elements left there, but we still had then 3 elements to choose as 1s. Okay, or had we choose a 1 first, we had 3 elements we had a length of 3 still to complete. We chose a 1, so we had 2 1s left. Okay, so then the cardinality of this set is the sum of the cardinalities of those 2 separate sets. And we can do that, we can add their cardinalities, because we are working with disjoint events. Okay, so we can keep going down. This should be good enough, but both B3 and 1, so we can now work out what we have for B3 and 1 and B3 2, B3 1, and these two over here. Okay, but what it's saying, we must pick one of the 3 bits to be a 1. Then there's 3 ways to do that. Or one of the 3 bits to be a 0, and there's 3 ways to do that in B33. Okay, or B31 rather, B32. These two over here. Also, B33 contains just 1 string. It must have a length of 3 and a weight of 3, so it can only be 1, 1, 1. So this has a cardinality of 1. That's set over there. Okay, B42 over here, we had B33 here, B31 and B32, B31 and B32 each contained 3 bit strings. So there's 3 possibilities here, and there's 3 possibilities depending on how I chose these to start off with. Okay, so there's 3 there, so the cardinality of this set B42 will then be absolutely 6. Okay, and B43, there's only one choice here that I can choose, and I've already worked out that B32 is 3, so the cardinality here is 3, so the cardinality of this set is then definitely 4, which puts the cardinality of B5 or B53 at a total of 10 different strings that we can string together that has a length of 5 and a weight of 3. But now we started with 32. Remember, initially, if we have 5 elements, initially we can arrange those 5 in 32 different ways. And 10 were the answers to counting the questions about subsets. Now, well, they're asking, is this a coincidence? And then they answer by saying, no, not at all. Each bit string can be thought of as a code of a subset, for a subset. So for the set 1, 2, 3, 4, 5, we could use 5 bit strings. So we could use B to the B5, okay, the length of the bit string, 1 bit for each element of 5. Each bit of the string is a 0. If its corresponding element in A is not in the subset, and a 1 if the element of A is in the subset. So if it's not in, it's 0, and if it's 1, then using the bit string, then it's in the subset. Remembering, deciding the subset amounted to a sequence of 5 yes or no votes for the elements in A. Instead of yes, we put a 1, and instead of no, we put a 0. So for example, the bit string 11001 represents the set 1, 2, 5. Why does it represent that? Well, there was 5 elements. If there's a 1, that element is included in the bit string. Okay, so 3 and 4 weren't, so that's why there's a 0 and a 0. So to represent that combination in a bit string formation, we'll say 1, 1, 0, 0, 1. Okay, since the first, second, and fifth elements are bits of it. The subset 3, 5 could be coded how? If that is a subset, 3 is in and 5 is in. So 1 and 2 is out. So 0, 0, 1, 0 for 4, and 1 for 5. 0, 0, 1, 0, 1. What we really have here is a bijection from the power set PA to the bit string with length of 5. And remember, a bijection is if and if only. Okay, so here, very important statement, and then we will conclude this short video. The statement says, now for a subset to contain exactly 3 elements, the corresponding bit string must contain exactly 3 ones. In other words, the weight must be 3 if it will only contain 3 elements. Read it again. For a subset to contain exactly 3 elements, it must have, so if its length is 3, it must have a weight of 3. Thus, counting the number of 3 element subsets of A is the same as counting the number of 5 bit strings of weight 3, which we have already done. Okay, so folks, that is concluding our bit strings. I'll put a few more videos down for you on the idea of counting with a bit string.